Physics Part 336. The direction of the force relative to the direction of the current and the magnetic field may be predicted using Fleming's left-hand rule. This is illustrated in the figure. If the first two fingers and thumb of the left hand are held at right angles to one another, with the first finger in the direction of the field and the second finger in the direction of the current, then the thumb gives the direction of the force or motion. Note that if the conductor is held fixed, the motion will not be seen, but nevertheless there will be an electromagnetic force. The magnitude of the electromagnetic force may be investigated using the current balance apparatus shown in the figure. A horseshoe magnet is made by placing two flat Magnador magnets on a U-shaped iron core. A length of the inflexible wire is firmly fixed between the poles of the magnet. When the current is switched on, the reading on the top pan balance changes. This change in the reading is a measure of the electromagnetic force. Variation of the current leads to the conclusion that the electromagnetic force F is proportional to the current I. By using Magnador magnets of different lengths but of similar strengths, the force F is found to be proportional to the length of the wire L in the magnetic field. Finally, by varying the angle theta between the wire and the direction of the magnetic field, the force F is found to be proportional to sine theta. Hence, the expression F is equal to F into IL sine theta is derived by the expression can be rewritten as F is equal to B into I into L sine theta, where B is a constant. The constant B depends on the strength of the magnet, and if stronger magnets are used, the constant has a greater value. The equation can therefore be used as the defining equation for magnetic field strength. F over L is equal to BI sine theta. So for a long straight conductor carrying unit current at right angles to a uniform magnetic field, the magnetic field strength B is numerically equal to the force per unit length of the conductor. Magnetic field strength is usually referred to a magnetic flux density. In SI units, this is determined in Tesla T. An alternative name for this unit is Weber per square meter, WBM square minus. 1 Tesla is the uniform magnetic flux density which, acting normally to a long straight wire, I beg your pardon please, carrying a current of 1 ampere causes a force per unit length 1 Newton per meter on the conductor. Since force is measured in newtons, length in meters, and current in amperes, it can be derived from the defining equation of Tesla that the Tesla may also be expressed as Newton per meter per ampere. The unit involves force, which is a vector quantity, and thus magnetic flux density is also a vector. When using the equation F is equal to BI into L sine theta, it is sometimes helpful to think